Just okay? Okay. First of all, I shouldn't say fun sheet. It was a fun sheet last year, but I just changed it to notes this year. So, don't kill sucks. Killed. That's terrible. Don't leave on my desk. Here we go.
Thank you.
Okay, you're welcome. Okay. So, first is a bit of vocabulary. It's hard to do implicit differentiation if you don't know what implicit means. So, implicit means kind of implied. Think of it implied versus explicit, which is not like, just think explicit lyrics or whatever. Explicit means clearly stated. Implicit, kind of hidden meaning or implied versus clearly stated. Now, in equation terms or math terms, it means is y isolated or not? So, for example, if I were to look at y equals 2x plus 3, y is isolated. It's by itself. It's explicitly stated y is this. It's an explicit equation. I could take that same equation, however, and put the x's and y's on the same side, and then what y is kind of implied within, but not clearly stated. So this is what would be called an implicit equation, where y is not isolated. You're following so far? Hi. Thank you. Was it a long test? That darn Baker. All right. So, would you please take a gander at each of these? Is this an explicit equation or an implicit equation? Implicit, because y is not clearly stated, solved for. What about the second one? That's an explicit, because y is clearly solved for. The third one? Y, I understand y is by itself, but isn't y is a mixture of x's and y's? Y is not clearly solved for all by itself, right? So it's not in terms of only the other variables. So that would be an implicit equation. Although y is by itself on one side, it's also mixed up on the other. And so it is an implicit equation. And the last one, it's implicit also. All right. Now then, today we've done derivatives of explicit equations. For example, this explicit equation, what derivative rule would you have to use? The chain rule. Yeah, yesterday we talked about how if you have a function within a function, you have to use the chain rule. In fact, the derivative of the inside would just be 1, so it wouldn't be crucial. But at any rate, we haven't done derivatives on the other types, the implicit equations. And it's a little more abstract, but if you follow along, it'll go well. My first caveat, though, is you don't ever read the Saxon book on how to do this, because it is an abomination of mathematics. All right? Please don't do it that way. I will vomit all over your paper if you do. Understood? Good. You don't want that. Now then, let's do it the proper way, which is to say, what the heck is this thing? Oh, shucks, that's not what I intended to do. Oh, wait, undo. No, do. All right. I don't know what this bottom thing is. It's ugly. Starting to understand the derivative of y term that's not just y. Use a chain rule. Now, this is why I can't understand that Saxon does this before the chain rule, but because you can't do implicit differentiation without the chain rule. Take the derivative of f of x squared, please, implicit or chain rule style. And so, what's the outside? The outside is the squaring, so it would be 2 comes down and drop it to 1, and the inside stays the same. And what was it before? It wasn't x before, it was f of x. Times the derivative of the inside, and the derivative of the inside is prime. That's the chain rule, okay? Now, in function notation, people tend to do better with that. Oh, I understand. Okay, take the derivative of f. That's f prime. Not all good. Imagine, though, if you took the derivative of y squared. It's pretty much the same. I mean, it's still squared. I'm just, instead of calling it y, f of x, I'm calling it y. You with me? Now, because it's the same idea, it should be the same. It just is a little different notation. this is where implicit comes along. You first take the derivative of the outside, which is 2 comes down, drop it to 1, and the inside stays the same. That's the part that groups people out. When I take the derivative of the inside, it's the derivative, or function, f prime. In y notation, we would call that y prime, true, but we're going to call it dy dx. Just like the other one above, I take the derivative on the outside function, which is y squared becomes 2y. But you have to take the derivative on the inside. And when you take the derivative of y with respect to x, think of it, don't overthink it here. When I took the derivative of this, what's this side? dy dx, yeah? I mean, when I take the derivative of y, I get dy dx, right? Same goes here. When I take the derivative of the inside, take the derivative of y, it's dy dx. Now, that then is the heart of what you're going to see in implicit differentiation. When you do implicit differentiation and you take the derivative on a y term, you're going to take the derivative like you normally would, the power rule and whatnot. But then on the chain rule part of it, you take the derivative of the variable itself and you're going to pick up a dy dx. That is the big idea. When you take the derivative of a y term, you take the derivative normally, but you gain a dy dx because of the chain rule. When you take the derivative of y with respect to x, you get a dy dx. Let me show you what this might look like. Say you had this here equation. It's not a function. It would fail the vertical line test, so I'll call it a relation. That's a relation. If I take the derivative with respect to x, then let's start off by saying I'm starting with the equation here, and I am taking the derivative of both sides. We have done this notation a little bit. The derivative with respect to x of this thing next to it, okay? That's mathematically justified because a derivative is just like adding to both sides of an equation, or subtracting, or dividing, or square rooting both sides of an equation. As long as you do it to both sides, you're cool, okay? I differentiated both sides. Now here's where we use our implicit differentiation. When I take the derivative of x squared, what is it? 2x. Derivative of the sum is just a separate derivative. So now I'm just going to add the next derivative. When I take the derivative of y squared, this is what we just did. When I took the derivative of y squared, I take the derivative of the outside, I get 2y, but then times the way y itself changes with x. So the derivative of y squared is 2y for the derivative of the outside, and then the chain rule for the inside, the derivative of y itself is dy dx. The derivative of the constant on the right is just 0, as always. Okay? Now, as opposed to these, where when I differentiated, boom, I was done because the derivative was already there. It just said, here's the derivative. Here, the derivative is in there. This is what I want. I want dy dx, but I want dy dx is this. So you need to then isolate the derivative term, solve for the derivative term. So if you isolated that, how would you do it? Subtract 2x and divide by 2y. Reduce if possible, and that's negative x over y. Now that also is new. A derivative with not just x's in it, but x's and y's in it. That actually makes a ton of sense once we look at the graph. But I'll pause for one question that everybody, or at least I definitely ask. I thought, well, when you do the derivative on this, okay, I got to do this chain rule thing on the y. How come I don't do it on the x? Why don't I do it there? Yeah, if I took the derivative of x squared and did a chain rule on it, the derivative of the outside is 2x, but the derivative of dx with respect to x is just dx dx. Okay, and so you could say you do the chain rule everywhere, you're consistent, it's just that when you do it on the next term, it's dx dx and it doesn't really show up. Do you follow? Okay, I'll take it. Actually, if you're saying, not really, then that's okay, you're in good shape. Let me show you, this is part of the beauty of math. This really has to be the case that the derivative is this way. Look at this graphically, and it'll kind of say, oh, yeah, that does kind of have to happen. What's the graph of that function? Or not function, excuse me, that graph. It's a circle centered at the origin with a radius of 3. Okay. Like that, yeah? All right. Now what we just did when we found the derivative was we found a rule that gives tangent slope everywhere, right? Are you with me? Okay. Now, why does this make sense? Let's consider why it has x and y in it. If I said take the derivative at x equal 1, would you be able to give me the tangent slope at x equal 1? Could you give me a tangent slope at x equal 1? No, it would be a problem because at x equal 1 there's actually 2. And you would have to say, I need more information. The derivative, the actual slope would depend on knowing both x and y. Not enough here. I would need to know x and y. So for example, if I told you, oh, I want it at 1 square root of 8, then you'd say, oh, you mean at that point, oh, I can find the derivative. Right? So it makes sense that the derivative would depend on x and y, because to find a slope at just x or just y wouldn't be enough information. I need both. Okay? Second, what about the signs of the derivative? If I drew tangent slopes here in quadrant 1, the tangents are always what? Those slopes, what do they look like? Positive or negative? Negative slopes. Well, that actually makes sense because in this quadrant, aren't x's positive and y's positive? And so if the derivative rule is the opposite of whatever x over y, in this quadrant, they'll always come out negative. So that's logical. In quadrant 2, if I have the derivative rule is the opposite of x over y, what are x's over here? Negative, and y's are positive. And so in this quadrant, derivative will always yield slopes that are positive. Does that make sense graphically? Yeah, in that quadrant, all the tangent slopes are positive. You can see then that the same holds true in all quadrants. If you have the derivative rule, negative x over y, and you put in a negative x and a negative y, which is what you get in quadrant 3, that's 3 negatives, those slopes would be negative, and that makes sense graphically. Those tangent slopes are negative. Therefore, you can see then the opposite of a positive x but a negative y would be positive slopes, and that also is all. Are you with me? All right. More then. Let's go about, what about the x and y axis? If I looked at the derivative at 0, actually let's go 3, 0. Notice here that the derivative, instead of just being at x equal 3 or x equal 2, the derivative is now at a point, x and a y, because I need an x and a y to run my derivative. What's the tangent slope at that point? It's vertical, it's undefined. A vertical slope is undefined. Right? Vertical. Consider that in terms of plugging into the derivative. What's negative x at that point? Negative 3 over 0 over y is 0, right? With me? Consider rise over run. This is vertical because this rises but doesn't run. There is no run. It's no vertical slope, yeah? Think about the slope or the derivative at 0, 3. I know visually the slope at 0, 3 should be 0. And does that make sense with the derivative when I calculate it? Visually, I know it's 0. When I go to calculate it, negative x over y is my derivative. So negative x is 0 over y is 3. Does that make sense then that I'm getting a derivative of 0 if the rise is 0 or there's no rise and there is run? If I went from here to here and didn't rise, just ran, I get horizontal slope. So would you write yourself a note here, because this will be a common AP kind of free response question. If you get non-zero, oops, I should start by identifying. If dy dx is non-zero over 0, then the tangent slope is, think rise but no run. What is that? Vertical. If dy dx is 0 over non-zero, that means there's no rise but some run. That is tangent slope horizontal, which makes sense. We already know from this week that if the derivative is 0, that's a horizontal tangent. All right, let's go back to implicit. That was just a side note on implicit that we often run into. But let's go back to taking an implicit derivative. So let's take one all the way through and see what this looks like, okay? So this is an implicit equation, and you're given the task of finding the derivative. The first thing we're going to do is when we take the derivative of each side, I don't particularly show this step, but I am really taking the derivative with respect to x of both sides. Because it's a sum, I can go term by term. What's the derivative of x squared? 2x. Now I suppose you could say dx when I take the derivative of the variable, but again, that's just 1. Plus, what's the derivative of y squared? 2y dy dx. Okay. Use the chain rule. The derivative of the inside is the derivative of y with respect to x. That's 2 dx, dy dx. What's the derivative of 2x? 2, and the derivative of 3y. 3 dy dx. Beautiful. Well done. 3 dy dx. And the derivative of negative 5? 0, and the derivative of 0 on the right side? 0. Okay. Now the goal is to get dy dx. Before, we only had one dy dx term. Now we have 2. So in this case, then, you're going to get all the, this is basic algebra kind of skills. You want to isolate dy dx. So you're going to get dy dx terms on one side, and anything that's not dy dx to the other. So if I move 2x and 3, not 3, 2, sorry. I think, at least the way I see it, these two guys are not dy dx terms. So I'm going to move them over there, right? The idea being that once I get dy dx is all on one side, I can factor out a dy dx because they all have a common dy dx and divide over it. So dy dx then is, at the end, negative 2x minus 2 over 2y plus 3. All right. Try that first one on your own, and let's see how that goes. Like always, if you want to do a rewrite above it, that's a good idea. You can go here. How do it? All right, so when you differentiate with respect to x, what's your derivative on the left? 2x plus 1/2 y to the negative 1/2, then dy dx. Beautiful. You take the derivative of the y term, you do the normal derivative, then you pick up the derivative of the inside, dy dx. And 0 on the 5, and the derivative of e to the y. E to the y, dy dx. Again, every time you take a derivative on a term with a y, you pick up a dy dx. Did you move your dy dx's? You have two dy dx's. Did you go all to the right or all to the left? All to the right. Yes. It doesn't matter. It's up to you. But if I move everything to the right, now in terms of the algebra, I am okay if you move all that over and simultaneously divide dy dx over. So if you had jumped straight to e to the y minus 1/2 y to the negative 1/2, I'm okay with that. Although if you did it in 2 steps, that's fine too. Dy dx then is 2x over e to the y minus 1/2 e to the negative 1/2 y to the negative 1. How'd you do? All right. You get it? Move on or try another one? Try another one. I don't buy it. I'll give you a second to think on that one. Go over it in a minute. How are we doing? All right, let's see how you did, shall we? Derivative of 2y with respect to x. 2 dy dx. So far, so good? Plus derivative of 3 root x. 3/2 x to the negative 1/2. Derivative of negative 1. 0. Derivative of sine y. Cosine y, dy dx. You're so smart. All right, so if I bring this bad boy over, it's up to you really, but 3, maybe I'll write this as that just for fun, although you don't have to. I would have cosine of y minus a 2, and I can factor out a dy dx. So check your answer. Do you have dy dx is, I don't know if I made my life better by that, 3 over 2 root x all over cosine y minus 2, or some equivalent. Yes? Okay, excellent. Let's talk how things get a little funky then. The ones that tend to cause students to make errors are then when you use chain rule, or sorry, implicit with products. So this one's got a product inside. You can see that once you get that x, y, things get a little more complicated, but if you just follow the rules, everything will be fine. So we'll do one together and you can try one. If I take the derivative on xy, because it's a product, I know I can't just say derivative times derivative, right? I have to use the product rule, which is first stays the same, so that's x. Derivative of the second is dy dx. Plus second stays the same. Y times the derivative of the first. 1, which you don't have to write. Okay. Minus 2 times derivative of y with respect to x. 2 dy dx. Derivative of 6x. 6, derivative of 9. 0. All right. Now I have parentheses enclosing my product rule. There's nothing outside. There's no sign outside. So do I really need those parentheses around my product rule? No, I really don't. Okay, so I can just forget the parentheses mentally and say my 2 dy dx terms, they're already on the left, so let's just keep those there. And when you take dy dx out, you'd have x minus 2 inside, yeah? What would you have on the other side? Negative y minus 6. And so in the end, the derivative, dy dx is negative y minus 6 over x minus 2. Say you were checking your answer with somebody else's, and they had y plus 6 over 2 minus x. Do you agree? Are we the same? Yeah, those are the same by virtue of if I multiplied by negative 1 over negative 1, which is totally fine, that's 1. Every sign. Now, if every sign is opposite, then you're golden, right? Try that one on your own, this product rule, in a second. I have my answer up there once you're ready. Check it out and see if you agree, disagree. It's a little ugly, so take your time, go slow, be careful. In terms of algebra simplification, I don't usually do it unless I have to make a multiple choice and see which one's equivalent. I don't care if you simplify fractions within fractions. So, do we agree with y squared plus 6 over 9 over y minus 2xy? All right. Okay, so where the first time I put this on a test, the success rate would probably be about 70%. The first time I put this on a test, the success rate goes down to about 40%. Now it seems like it's pretty well the same. It's got an implicit thing. It's got a product rule. This one little difference makes all the difference. People blow that negative for whatever reason, just carelessness really. A negative in front of a product tends to be, just a bridge too far. It pushes people over the edge and they start to make mistakes. So let's look at that. Be very careful with how you treat the negative. There are a couple of schools of thought how to do it. We'll talk about it. Let's take the derivative of 7 cosine x first. Easy enough. What is it? Negative 7 sine of x. Now, in terms of the negative, you have two choices. You can either say, forget that nonsense. I'm going to leave the negative out front and just run my product rule on the positive. Now that works fine, and it tends to minimize mistakes. The drawback of that is then you have to distribute the negative to get the dy dx terms together. So it usually means one more step. No big deal. You can kind of think of this as a plus and think of that negative as part of the x cubed term and keep that in terms of your derivatives and include the negative inside your product rule. So does either way of those appeal to you? Do you care about either way? The negative all the way out front or the mix in the negative? Out front. Okay, that tends to be less mistakes. So let's do that. So I'm just going to say, all right, I'll deal with the negative later. I'm going to do the product rule. What's the derivative on that product? X cubed, first stays the same. 2y dy dx. Plus second stays the same. Y squared, derivative of x cubed. 3x squared. Dx dx is just... All right, now moving on then. Plus 3x's derivative. 3 and negative y's derivative. Negative dy dx, right? Or negative 1 dy dx. Sweet? Okay, so let's distribute the negative and start moving stuff around. Negative 7 sine x minus 2x cubed y dy dx minus 3x squared y squared plus 3 equals negative dy dx. I just distributed the negative. You follow? dy dx is on the left or the right? The left? That's going to be so much moving. Let's move them to the right, shall we? Okay. I didn't mean to really give you a choice. If I knew you were going to choose badly, I wouldn't have let you choose. Negative 7 sine of x minus 3x squared y squared plus 3 stays on the right. They're already on the right, so let's just leave them there. The dy dx terms, once I get them all on the right side, I'll factor out a dy dx. What's on the right side inside the parentheses? Negative. Negative. Negative 1. What's here? When I take out dy dx, what is it? Negative 1. And then what's here once I move it over? Plus 2 x cubed y or yx cubed, however you, obviously you know the commutative property and all that applies. So you could have that order different. 2x cubed y minus 1 is fine. But at the end of the day, dy dx is all that stuff, negative 7 sine minus 3x squared y squared plus 3, all divided by the quantity negative 1 plus 2x cubed y. You follow? All right then. Last but not least, you're going to use this skill when we get to related rates. All right? So imagine, if you will, that instead of just a stone cold circle, you are dealing with a Ferris wheel. All right? And you're on this Ferris wheel with your girlfriend or your boyfriend or whatever, and you're going this way. At any rate, the vertical and horizontal position, I could locate where I am horizontally at any time on the Ferris wheel and where I am vertically at any time. But it doesn't really make sense to relate them to each other, horizontal versus vertical. They both really are affected not by each other, but by time, when you are where you are, okay? So it's often the case, especially when we get to parametric equations, that instead of relating y to x, you want to relate them both to time. Now, if then I want to talk about how I'm moving horizontally, then that's movement, and you're talking about change in horizontal position, not with respect to change in y, but with respect to change in time. You want dx dt. So consider if this equation was the case. That's a circle, not centered at the origin, and you wanted dx dt. To get dx dt, the denominator here implies I want to take the derivative with respect to time. I want to see, in plain old English, that means how does x change as time moves on, as time changes? Or how does y change with time, not with each other? So take derivative with respect to time. if I take the derivative with respect to time of both sides of the equation, then I'm actually going to get, instead of just one type of differential term or dy dx term, I'm actually going to get a couple different types. When I take the derivative with respect to time of x squared, I take the derivative of the outside, which is 2x, times the derivative of x with respect to time, which is dx dt. Now the derivative of the next term, the derivative of y squared with respect to time. 2y, the derivative of the inside then, dy dt. Derivative of 2x with respect to time. 2 for the derivative of 2x, then times the derivative of the inside, dx dt, plus the derivative of 3y. 3 dy dt, derivative of 5 with respect to time. Well, 5's constant, doesn't change, so it's 0 and 0, right? If I want dx dt, then that's dx dt, and that's dx dt. I want those. Everything else, I don't want. Now, this is going to be different because your derivative is going to have derivatives over here with it. So that's okay. If I collect the dx dt's, I would have 2x's plus 2 of those. Everything else, I'm going to move over to the right side of the equation. So that is 2y dy dt and 3 dy dt, and those both have a dy dt, so you could definitely factor out the dy dt. You don't have to. What's important to me is that I isolate dx dt. So it is, these are negative, yes. Is that what you're saying, Sarah? Well, why didn't you say so louder? Have more faith in yourself. Negative 2y dy dt minus 3 dy dt, all divided by 2x plus 2. Okay. Now that's a related rates problem you just did. It doesn't, we didn't have a word problem attached to it, but that's going to be something we'll do. It's super fun. All right, that's implicit, at least a good start. You kind of have a clue? Okay, I'll take it. Kind of a clue is a good start to implicit differentiation. Last night's homework, how did it go? Here's the homework for you back. I remind you, if you get help from me or from somebody else, it should be showing up in color. So a gentle rebuke for you here. This problem on last night's fun sheet 3, number 13, where it said, find the value of k where it hits the axis 3 times. I see a lot of people with pencil. Most people have pencil there. I'm sorry, I don't buy that. I gave that to the BC kids, and I had maybe 3 of them smoke it. I don't buy that you all got that without. I don't buy it. Sorry. So you must show that you got help on that by using ink. All right? In the future, as soon as I get fairly caught up and I don't get this huge lesson, I'm going to drop a homework quiz on you, and you're going to want it to be in ink, okay? All right, you don't need my folder. Take my folder for it. All right, that's good. All right, questions on last night's homework? If you have any, did I put the key up? Do we still? You don't still have 33, do you? Did we turn in 33 yesterday? Okay. So the chain rule. Do I need to put up my answers, or you access the key? You don't need to see them. Let me. I'll tell you what. Let me put them in here, and anyone that you want to ask about, we can ask about. That's not it. Doggone it. Chain. Where's the chain? Chain rule. Chain rule.
I just went away with that. I knew he was going to go. Oh, yeah.
All right. All right, my bad. Okay, how about the first 9? Do you want to talk about any of those first 9? Which one? 16? Okay, jump to 16 then. I'm glad for any questions. 16. Okay. So 16, horizontal tangent. Remember, horizontal tangent means where the derivative is 0. So I need to take the derivative, then find where it's 0. So I really have 2 issues, calculus issue, then the pre-calculus issue of solving it. Let's start with the derivative. Why is this a chain rule problem? Because I have a function within a function. That's when you use a chain. What is the outside here, log or sine? Log. So if I take the derivative of the outside, I take the derivative of the log, which is 1 over x. Now normally I would say 1 over x, but I really mean more generally it's 1 over whatever's inside the log. So what's inside the log? Sine, right? Chain rule says take the derivative of the outside with the inside still in, then times the derivative of the inside. Now I'm to the derivative of the inside, which is the derivative of sine, and that is cos. Okay? Now, I need to, that's my derivative. Notice that the derivative is cotangent. Cosine over sine. That would mean the antiderivative of cotangent is log of sine. Yeah. Okay? Crazy. At any rate, I want to find where this is 0. Is this going to be 0 if the top is 0 or the bottom is 0? The top. If the top is 0, it's 0. If the bottom is 0, it's undefined. So I need to just focus on where is cosine 0. Remember, cosine is x, so x is 0 when you go straight up or straight down angle-wise. So your 2 solutions are x equal pi over 2 and 3 pi over 2. Radians, always radians, not degrees. Does that make sense? Okay. Other questions? 15? Okay. 15. Function is increasing. The big idea here is increasing if the derivative is positive. If something is increasing, then if you draw the tangent line to any point in a curve like that, the derivative is positive. So you need to find where the derivative is positive. First, we'll need the derivative. Then we'll need to see where the derivative is 0 to see, 0 is where positive starts and stops, where you switch over from positive to negative. And then we'll sign test. That's my plan. What's the derivative using the chain rule? E to the x squared plus x for the derivative of the outside, and then times 2x plus 1 for the derivative of the inside. Derivative of x squared plus x is 2x plus 1. Now we're going to set that equal to 0. Can e to any power ever be 0? It cannot. E to a power is always positive. All right? So that cannot yield any zeros. What about 2x plus 1? Where would that be 0? Only at negative 1/2. All right? You see where I'm coming from? Okay. Normally I'd have a product, I'd say where does each one equal 0, but an exponential can't be 0. In terms of sign test then, I'm going to sign test my derivative before and after negative 1/2. Before negative 1/2, say negative 2. E is always positive. What about if I put negative 2 into the 2x plus 1? That would be negative. So overall, this product or the derivative is negative in that region. what's going on with the function? If a derivative is negative, then the original function must be decreasing. If derivative negative means negative slope, and that means decreasing. Okay? We know the derivative is 0 there, so the graph goes flat at negative 1/2. And then after negative 1/2, say at x equals 0 is a test point. E to the 0 is positive 1. 0 plus 1 is positive, so the derivative is positive. On that side, then, the function is increasing. If the derivative is positive, the tangent slopes are positive, the function must have been increasing. So to answer the question, and I'll throw in some justification for good practice, f is increasing on what interval? Negative 1/2 to infinity, because what? Why do you say that? Because f prime is positive, okay? I'm, for the most part, pleased with how your justifications are going. I had at least 2 people, however, use pronouns. If you say it at any place, you will be losing points, no doubt about it. There is no it. Pronouns are never used. Because it is positive is worthless. All right? It's because f is increasing because f prime is positive. Never use a pronoun. Other questions? Okay, cool. I'll just walk around. Let me know if I can help you. There are a few implicit problems on tonight's homework, and there's a few chain rule problems on tonight's homework. And do pay attention to, if you're doing the product rule right and stuff. I'm having people turn in problems with the product rule wrong. You should know whether you're doing it right or not. Let me know what I